Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, we have the pleasure of having François Potier visit us today from Invariant. François' interests include ML type inference, among other things, and also program proof, and this is the topic of the talk today. He's going to tell us about a verified implementation of a union find algorithm, both in terms of functional correctness and algorithm complexity.
Thank you. And thanks for inviting me to visit RISE. I'm very happy to be here. So this is joint work with Arthur Charguéraud, who's also a researcher at INRIA. And as Jonathan just said, this is a kind of case study in proving a small piece of CAML code, both in terms of correctness and in terms of time complexity. So we picked union find as an example that's interesting to us because it's very useful. It has many applications in compilers and theorem provers because it's at the heart of first-order unification in particular. And it's also interesting because it has a very tricky complexity analysis which has been simplified over the years, beginning with Tarjan's analysis in '75. And so we wanted to see if we could port this analysis to a machine-checked, make a machine-checked version of it. So I'll begin by recalling briefly what union find is, how it works. It's a data structure for maintaining equivalence classes under unions. So I'm guessing most of you have seen it before. It's also called a disjoint set forest, where every element either is a root, like this, or has a pointer to some other element. So it's got a link. This one, for instance, has got a link to a root. And each of these trees forms an equivalence class whose representative element is the root. And the OCaml API, which you can offer for this algorithm, is this, where there is a type of elements and 3 basic operations to create a new element, find the representative element of an arbitrary element. So find will just follow the links all the way down to the root. And union, which takes typically 2 roots as argument or 2 arbitrary elements as argument. And if you give it 2 roots, for instance, it will install a link from one to the other. And there is also an operation not shown here for testing whether 2 elements are in the same equivalence class. So the code for this thing is very simple, and that's one of the reasons why we chose this example. It fits on a slide. And I'm not going to read everything, but the few things which are worth noticing are that every element is mutable. It's a reference to some content, and the content is either a link to some other element, so a pointer to some other element, or if we have a root, then we carry an integer rank, which is used to do balancing. When we union 2 roots, the rank helps us decide which way the pointer should be installed. So the balancing is visible here, where we compare the ranks. And another thing that's worth noticing is the find operation. So it's written as a recursive function which just follows the pointers all the way to the root. And the interesting line is this thing here, which installs shortcuts. So it's path compression, where we modify the forest as we walk it so as to make the next find operation more efficient. So it's the combination of balancing and path compression which gives the very good efficiency where find and link and union have almost constant time complexity, at least if you reason in terms of amortized complexity. And in the worst case, it's logarithmic. So the complexity analysis was first done by Tarjan in '75, and at the time the paper published by Tarjan was quite complicated. But it's been simplified over the years by Tarjan himself and by others, including Kozan. And you can find a very simple proof today, either in the textbook I have cited here or in some course notes which are available online by Tarjan. And so the paper proof is about 3 pages and it's very easy to follow, at least if you are happy with checking that it's correct. Because it's quite difficult to understand why it makes any sense and how they came up with it. But at least if you just follow the steps, you can confirm that everything is correct fairly easily. And so the main result is that the complexity of union and find is O of alpha of n, which means almost constant in practice, because alpha is the inverse of this function a, which grows very, very quickly. So the things I want to talk about today are some details of the specification of union find and how the specification talks about what it does and how much time it needs at the same time. We'll see. And also one point I want to emphasize is that we're not just making a proof of the algorithm based on some pseudocode, but we are actually looking at the OCaml code, which I just showed, and we prove that this particular implementation is correct. And this is modular in the sense that we establish a rather simple specification which a client could use if we had for instance, a unification algorithm could be proved correct based on this specification. I should say that if you want to ask any questions during the talk, you shouldn't hesitate. So the way we do this is we use CFML, which is a tool developed by Arthur. It's embedded inside Coq, and it can be used to reason about OCaml code. So at the same time, it's a library and a tool. The tool takes the OCaml code and turns it into a Coq formula, a Coq description of the behavior of the OCaml code. And then there is a bunch of Coq lemmas and Coq tactics which you can use to actually reason step by step about the code. So essentially it's a whole logic or a separation logic where you have preconditions and postconditions and you prove that the code satisfies them. I should say briefly that there is a lot of related work on proving programs correct, and of course I'm not going to mention all of it here, but much of it is mostly concerned with functional correctness and does not look at complexity at all. And if you look at the previous work that does include complexity concerns, then often they are concerned only with the mathematical level and not with the code itself. And also often they're concerned with inferring the complexity completely automatically, whereas here we're not trying to infer anything at all, we're just trying to do a manual proof. And this little corner of the literature where we fit has been relatively little explored, I think. Most people have tried to fit in one of the other niches, but we are almost the only people, I believe, to have looked at manual proofs of complexity. And of course, so it's manual, so it's a bit painful, but it can be very expressive. For instance, proving this alpha of n complexity is something which no automated tool could hope to do, because there is a proof which requires a lot of human ingenuity, and there is no way you could do it automatically, at least with today's tools.
Did you say that the original program is translated into this framework?
Yes, the OCaml code, which I showed here, is translated by the CFML tool into what Arthur calls a characteristic formula, and that's a kind of description of the behavior of this code. Sorry?
From his thesis?
Yes, from his thesis, yeah. And so then we establish a whole triple about this code, so a pre-post condition pair.
And that translation by itself, that you have to trust?
Yes, you have to trust that the tool is correct. Yeah. So this has been proven on paper, but of course there could be a bug in the paper proof or a bug in the implementation of the tool. So you have to trust this part. There was another question.
About
verifying computation complexity. There was also Niels Anders Danielson doing
yes.
in AGDA doing verified lazy data structures.
Yes, there was this paper at Popular 08
Yes,
by
yes.
Niels Anders Danielson. And indeed, he would fit in the same niche as us. I think he didn't try to automate, but he had quite a lot of expressiveness because he could use AGDA as a theorem prover to do interesting proofs of complexity. And indeed, he focused on the use of thunks and lazy evaluation. So first I'll show the specification which we prove. So that's what we show to clients of the Union Find module. And then I'll say some words about the framework which we use, separation logic extended with time credits. And if there is time, I'll say a bit more about the proof itself and the invariants which it uses internally. So the specification, since what we use is essentially a whole logic, a separation logic, we equip every operation with a precondition and a postcondition, and that's what we show to the clients. So the way we write these things is maybe a tiny bit unusual, but that's because we have to fit in Coq's syntax. But this is the way we write the specification for find, for instance. This line here is the precondition, and the last line is the postcondition, where R stands for the result returned by find. So what this says roughly, well, the precondition says you have to have a well-formed union find data structure before you can call find. And so this UF here is an abstract predicate, which means there exists a well-formed union find data structure, and I am the unique owner of it. Since this is a separation logic, we follow the usual discipline of separation logic, which says that when you want to mutate a data structure, you have to be the unique owner of it. So that's what UF NDR means. And the parameters NDR are explained down here on the slides. D is the set of all elements, so the set of their memory addresses, if you will. So that's the domain of the union find data structure. N is a bound on the number of elements. I'll speak about it a little bit later. You have to fix it at the beginning. It's used only in the complexity analysis. It doesn't really exist at runtime or play any role at runtime. And R is a logical level function which maps every element to its representative element. It doesn't really exist at runtime either.
In your definition of the union find structure, usually one has contents of alpha, where alpha is some.
Oh yes, that's a good remark. Indeed, we were a bit out of time when we rushed to publish a paper about this, so we had to leave out the alphas. But you're right that usually you would attach a datum of some type alpha to every root, and then the type LM would become type alpha LM, and find would return maybe an alpha, or maybe you would have another operation besides find, which would give you the datum attached with an equivalence class. So it wouldn't be much more difficult, I guess, maybe one more day of work to adapt this. And we plan to do it. Yeah. So here indeed, because we don't have these datum, these data elements, what find does is just return the representative element. And that's what the specification says here. It says this thing will return an element R, such that R is the representative of X, and the union find data structure will still be well formed after that, and you will still be the unique owner of it. And then the interesting aspect here is this $alpha of n plus 2. So $, is our notation for time credits. So it's a permission to spend 1 unit of time, basically. And here what we are telling the client is you need to give us alpha of n plus 2 credits when you call find, and that's the advertised cost, so to speak. So it's the amortized cost. And as we'll see, maybe the real cost will be less than that or maybe more than that, but that's our business. We take care of that internally. The client doesn't have to know. All they have to know is they have to give us this amount of credits.
You have some notion of saving credits from one invocation to another?
Yes, yeah. I'll say a bit more about that later on.
Why do you need the star? These are the things on the right of the star are pure predicates, right?
This one is not really pure because these credits are affine, and so when you say $n credits, it means I own these credits. I am the unique owner of them, and maybe I'll consume them, and then they'll be lost forever. So the first star is really a star of two impure assertions. And indeed, this one between brackets, so those square brackets are the syntax for pure assertions. So this equation is something that does not represent the ownership of anything. It's just an equation.
So you could have used just a normal conjunction instead of the star?
Yes, here we could use a normal conjunction.
Okay.
But I don't think we have it. We never use it, I think. We just used star everywhere. And the other operations have analogous specifications, so I don't think we need to read them in detail. But again, we'll see a precondition and a postcondition. And again, we see the number of credits that must be passed in. So this one happens to require 3 alpha of n plus 6 credits. And that's a bit more concrete than we would like. Of course, we'd like to say it's O, big O of alpha of n. And we have begun working to work with big O's, but it's not quite ready yet. So at the moment, I'm just showing these concrete specifications. And maybe one would also like to publish a spec which says something about amortized complexity and worst case complexity. So here the worst case complexity is O of log n, and the spec doesn't say it. If we wanted to say it, we would need to have maybe another kind of time credits which cannot be stored from one invocation to the next. So then we could say we require O of log n non-storable credits, and that would be a way of saying that the worst case cost is O of log n. This is the function make, which creates a new point. So this one just has constant time complexity. And yeah, there is this precondition here, this condition which says the cardinality of the domain should never exceed n. This is kind of unpleasant, but it's imposed to us by the way the proof is written, the textbook proof which we follow. It has this parameter n which needs to be fixed at the very beginning because it plays a role in the definition of the potential function. And this is where we see, this is where n is fixed, and this is also where the UF predicate is created out of nothing. When you want to begin using the algorithm, initially you have nothing. But you can say, I'd like to begin working with an empty union-find data structure, and this does nothing at runtime actually, because you don't need to do anything to initialize the structure. So it's just a theorem that we proved, and that says if you have nothing, then you can turn that into an empty union-find data structure with an empty domain. And at this point, you have to choose n, and it's going to be fixed for the remainder of the use of this data structure. So this is not very, having to fix n like this is not very convenient. And there is actually a recent paper which was published last year where they are able to avoid this thing, and we hope to adapt their proof in the future.
You make n arbitrarily large with no bad consequences. I mean, is there any reason?
You mean here, or?
Yeah, here.
Yeah, here you can choose any n you like, and it's only used in the complexity analysis. It doesn't have any use at runtime, so you could choose. No, n isn't used at runtime at all. Yeah, it's used in the complexity analysis. So indeed, it is used. It appears in these preconditions, but it doesn't influence the actual runtime. It's only used in the analysis. Yeah, so you could use, I don't know, but something like the age of the universe for n, and it would give you alpha of n equals 5, and basically in practice you would be happy.
Could that be captured in the spec somehow by saying n is a ghost in that or something like that?
Yes, well, it is ghost, if you will. Just like D and R, these things appear only as parameters to the abstract predicates, but they don't appear in the code itself. So that's the way we manipulate ghost state.
So you mentioned someone else did without the n. Could you have just incremented n if the cardinality of v exceeded n? I mean, just
well, in the proof we follow, it's hard to change n somewhere in the middle because you have defined a potential function which depends on n. You have carefully arranged just the right number of time credits everywhere on every element in your data structure. And if suddenly you change n, then you may have to request new time credits and then put them in your data structure. So it's not easy to see how to do this. But actually the paper I mentioned does this. It requires some subtle changes to the proof. So again, it doesn't look very hard, and once these guys give you the right approach, but finding it is very difficult, I think. So I'll say a few more now about the logic that we use. This slide is supposed to recall basically, well, some definitions of separation logic. The assertions that we use are implicitly parameterized over the heap. So heap to prop means there are propositions which refer to a heap or a heaplet. It's typically a partial heap, only the part of the heap that you own. And you don't need to really to read this. These are the definitions of the usual connectives, and in particular, separating conjunction says the heap should be splittable into two compatible subheaps, and H1 should hold of one of them, and H2 should hold of the other. So these are basically the definitions which you find in every paper on separation logic everywhere. And the basic CFML framework uses these definitions. What we want to do now is extend it with time credits, and somehow we have to explain what $n means. So to do that, well, first, let me see what we would like to have. We would like to have $n as a new connective, a new kind of assertion in separation logic. So we would also like it to have type heap to prop. And the properties that we needed to satisfy are very few, only these two basically. So 0 credits should be the same as true, as nothing. And we would like to have this equation here which says that if you have n plus n prime credits, then you can split them and use the two parts for different purposes. Maybe pass n credits to a function which you're calling and use the rest for yourself later on. Or maybe store some of them in the heap for later use and keep the rest to use now, or something like that. So that's basically the only properties that we need. And we also need somehow to tie the meaning of these time credits to the actual computation mechanism. We need to say that whenever you perform one step of computation, you need to consume 1 credit. So first I'll say how we define $n, how this predicate. It just says that, well, there is a kind of, you can think of the heap as containing a special memory location where there is a certain number of credits that is stored. So to say that, we're changing the type of heap. It's not just going to be a map of location to values, but we will add to it this special memory location which contains an integer, and it's the number of credits that are still in existence. In that case, $n just means that this memory location, this ghost memory location, contains the value n at the moment. And again, this can be a partial count in the same way that a heap can be a partial heap, which represents only the part you own. This n here can typically represents only a number of credits that I own, and maybe some other people own more. And this is reflected in the definition of separating conjunction, where you see we have a plus here. So this basically means different threads can hold different numbers of credits. Yes.
Might there be algorithms where it would be useful to have it be a rational number at some locations?
Maybe it could be a rational number, yeah, or even a real number. At the moment, we've been working with integers, and this doesn't prevent you in some proofs from using rationals or reals to reason about how many credits you have. But we thought it would be simpler to make it an integer in this model. It could be real too. For the moment, we don't have many, we haven't done many case studies yet, only 2 or 3 besides this one. And for the moment, working with integers has always been sufficient. Okay, so to connect these time credits with actual computation steps, what we say is very simple. It's just every function call consumes 1 credit. And if there are any loops in the program, we just view them as recursive functions. So we only need this rule. Every function call costs 1. And also we provide no way of creating new credits. So you have to think that at the beginning of the program, of the program's execution, a certain number of credits are given by God, so to speak, and you can only consume them. You can never create new ones. So intuitively, it should be easy to see that the total number of function calls that are ever performed by your program is bounded by the initial number of credits that you provide, which intuitively means that this initial number of credits is a good measure of the complexity. So this particular inequality we prove on paper. So we have a precise statement, which I'll just skip, but we can prove it on paper in the same way that we prove the correctness of the logic, the CFML logic.
So yes. What you're counting is the number of calls to your API functions, such as link.
Every function, basically.
Every single function?
Yeah, including any auxiliary functions that you may define inside your module.
So what about assignment? Is assignment a function?
You can consider it as a primitive operation and say it costs 0, or you could consider it as a function and say it costs 1. In the end, it doesn't make any difference, of course. Well, it makes a difference in the concrete count of credits, but asymptotically, it doesn't make any difference. Intuitively, one might think that it would be sufficient to say every recursive function call costs 1 credit, but since we are in a high-order language, we don't really know ahead of time which functions are going to be recursive, which functions are going to call each other. So it's simpler to just say every function call costs 1. And the way this is done in CFML is that conceptually CFML with time credits, it will just insert a call to pay at the beginning of every function, for instance, and then everything will proceed as in the old CFML without time credits. You only have to consider that this pseudo function pay has $1 as its precondition, and that will force you, when reasoning, to pay 1 credit every time you come across this call to pay. So that's how it's implemented, I think.
So it looks like you're not allowed to go into depth. You can't say, well, if I have an infinite sequence of these operations, I will eventually amortize it. You have to save in advance to pay things later.
Yes, if you want to amortize, you have to save in advance. So I guess this means we do potential-based proofs of amortized complexity. And some paper proofs don't fit in that framework because they want to consider the whole sequence of operations at once. And for instance, I know of a paper that reasons about union find in a divide and conquer manner. And so it reasons about whole sequences of operations. And And this kind of proof we would not be able to port directly. Another thing which you may have been wondering about is it okay to just count the function calls? In what sense is that a meaningful measure? There are two assumptions which we're making here. And one of them is that if you have an OCaml function which doesn't contain any loops, then the compiler which will translate it to some assembly or machine code that doesn't contain any loops either. Which means that the cost of invoking this function is basically a constant. It can itself, of course, do some other function calls, but those will be counted. So there is basically here a constant factor, which is the size of the largest function body in your assembly code or something like that. And the other assumption is that every machine instruction executes in constant time for some constant. So some people may throw their arms in the air and say this is crazy, but of course some machine instructions take much longer than others, but at our level of abstraction we'll just say it's a constant. So if you accept these hypotheses, which we cannot really prove because that would require a detailed model of the compiler and of the machine, if you accept them, then you get that the number of credits which are spent is really up to a constant factor, a good measure of the time that's required to execute the program. Yeah, and this I mentioned already in passing, but these time credits, they're ordinary separation logic assertions. So this means you can pass the ownership of a certain number of credits from a caller to a callee, or even back. And also you can store them in the heap. And we'll see that in the union find example, where when we look at the definition of the UF predicate, we'll see that it says several things. And among others, it says, I own a certain number of time credits. That's the credits that I have saved ahead of time to be able to justify that the amortized cost of every operation is correct. Okay, so this leads me to the last part of the talk, where I'm going to say a few more words about how we define UF internally in particular, what it looks like. So UF is a conjunction of four things. Well, the definition looks like this, and I'll explain in turn what these four things are. I don't think I have to go too deep into the details. I just want to say roughly what this is about. So the first part of the invariant is what you would find in a mathematical proof. If you were reasoning about the pseudocode and not the actual code, then you would need to say some things like the disjoint set forest is balanced in some way, and the ranks which are stored on the nodes satisfy certain properties. So that's the kind of thing you have to write here. If I read just one, yeah. This capital F, which hasn't appeared yet, is the graph. It's a relation between nodes, and it tells you when there is an edge from one node to another. So this particular line here, for instance, says if there is an edge from X to Y, then the rank of X is strictly less than the rank of Y. So that this says the rank grows strictly as you follow paths in the graph. So that's one example of a property which you need to track off. It needs to be part of the invariant. And so K is this function which maps every element to its rank. And it's also ghost state in a way. If you recall the OCaml code, in the actual executable code, we only keep track of the rank of every root. For the internal nodes, we don't need to keep track of the rank. Whereas in the proof, we need to keep track of the rank of every node. And that's not a problem. It's permitted by this approach. The second part of the invariant is the ownership of the part of memory where the nodes exist. Since this is a separation logic, we want to say we are the unique owner of this part of memory. CFML gives us a predicate called group ref, which represents a region or a group of references in the heap. And it's parameterized by a finite map M, which maps every memory location to its content. So in the invariant, we are going to have an assertion of this form, group ref M. And then we need to connect the first two things that we just saw. On the one side, we had the mathematical reasoning, and on the other hand, we had this group ref assertion, and we need to say what's the connection between them. So that's what this third part is about. We have to say that the domain of the map M, which exists in memory, is in fact exactly D, the D that appears in the mathematical invariant. And we also have to connect the content. So we say that for every x in there, M of x is a link if there is a link in the graph, and M of x is root if x is a root in the graph. And we also say that if it's a root, then the rank that exists at runtime is the rank that we keep track in the mathematical part of the proof. So this is the usual way of connecting what happens at runtime with what happens in your reasoning. It's the representation predicate. And the last part of the invariant is the potential. So here we follow the textbook proof about the amortized time complexity. It's the potential-based proof. So there is this potential function phi, which tells us how many time credits we should have at hand at every point in time. So it's a function because it depends on many things, d, f, k, n, and so on. So in Coq, we will have to define this function phi. And as part of the invariant, we will have to say we hold phi time credits. So that's, to sum up, that's how UF is defined. It contains the mathematical invariants, the ownership of the references, the predicate that connects the first two aspects, and the appropriate number of time credits. And once we have given this definition, then we only have to check that every operation satisfies its specification. So it takes, typically every operation has UF as a precondition and UF as a postcondition, so we will have to prove that this invariant is maintained. The definition of phi is very tricky. I'm not going to read this in detail. The question here is, how did they find this thing? And I think it's quite hard to understand the historical process by which they came to this. But some intuition is given by this paper here, where they have an approach which is not based on a potential function. It's based on looking at the whole sequence of operations and using a divide and conquer argument to find a recurrence equation that describes the overall cost. So this paper is, I think, illuminating to some extent, but it's not directly amenable to our style of reasoning. So we have to follow the paper proof based on the potential function. And this one, unfortunately, doesn't seem to carry any interesting intuition, at least for us. Maybe for Tarjan it does, but...
So there's no general way of, or someone would have found it by now, of converting a proof of about a sequence of operations into a potential fix. If you're allowed to get a constant number of credits at the beginning.
The problem is we are in this whole logic approach where we have to give a pre and a post to each operation. And if you do this, this forces you into a very local view where you reason about one operation at a time. So I don't know if it's possible to remain in this framework and at the same time be able to reason about a sequence of operations. Maybe it's possible, I'm not sure. That said, if you want to reason at the level of the pseudocode instead of the actual executable code, then I guess you have more flexibility and you can reason about a sequence of operations. There was a paper this year by Tobias Nipkov at ITP where he did some proofs of amortized complexity at the level of the pseudocode, and I think he allowed himself to reason about sequences of operations. So coming back to these things, basically we translate them directly into Coq. It isn't very readable, but it says the same thing essentially. We use, for convenience, we don't limit ourselves to the constructive subset of Coq, so we allow ourselves to use epsilon operator, for instance. It's used here because here Tarjan says, let P of x be the parent of x if x has a parent. And this seems innocuous, but really you cannot translate it into Coq without using the epsilon operator, or maybe iota operator, the unique choice operator. Because if x doesn't have a parent, then this thing doesn't make sense. So you must allow yourself to say, let P of x be this expression if it is defined. And if it's not defined, then P of x is anything. It could be any node. Yes?
Would you need that if you just said P of x is defined to be the parent of x, or like x itself?
Yeah, maybe you could give a default value. Yes. But then you would need this if. Yeah, you would need this if, which is another thing which we use, which is also non-constructive. In Coq, usually you cannot say if on a proposition. You can say if on a Boolean, which is not the same thing. So if you want to say if x has a parent, then this, else that, you need an if which takes a prop as an argument, and this requires, it's essentially the excluded middle or something like that. So it's another feature which we use here. It's this capital if which takes a prop, and that's also not part of the constructive subset. Okay, and the last thing I'll say is, well, you don't want to look at the proof in detail. It's a bit hairy. But what's interesting is just the way that what you have to prove, which is this inequality, arises naturally just because you have to prove that the UF invariant is preserved. So initially, as part of UF, you get a certain amount of credits, phi. You also get the credits which are brought to you by the client. For instance, if we are verifying find, the precondition says the client should bring alpha of n plus 2 credits. So you get these credits here. And using all of that, you're supposed to, well, you will have to consume some of them because you are making some function calls. So that's the actual cost. And then you will have to prove that you're able to reestablish phi, the invariant, in the new state, in the modified state. So that's the phi prime term, which is here. So that's what that's the inequality which is proven in the textbooks, and here it just arises out of the methodology which we follow. And that's about as much detail as I wanted to show about the proof, but I can show more details offline if someone's interested. So in conclusion, we're happy with the result because the proofs, the textbook proofs, were relatively easy to port, and we think it's nice to be able to write a whole triple which says something about correctness and complexity at the same time. And we think it's good to be able to reason about the actual code rather than some kind of abstract pseudocode. And the whole thing is relatively short. It's about 3,000 non-comment lines of proofs for the mathematical arguments, and then about 400 lines of code for the specs and the equivalent of the VC-gen process. So producing the proof obligations, which F star, for instance, would do automatically, or Daphne. In this case, you have to do it step by step by using Coq tactics, but it's quite concise usually, so it doesn't take a lot of space. You can find the proofs online. And in the future, some things we'd like to do, so this I mentioned, it's establish a more precise bound which doesn't force you to fix a capital N ahead of time. So in practice, of course, alpha of little n and alpha of big N, they are both constants for any reasonable human use, but it's convenient not to have to fix capital N for the client. Also, we'd like to introduce this big O notation. Nikhil mentioned this. And this could be, well, it's one case study which will be part of a larger project that's just now beginning, just about to begin. We have got some funding to try and develop a verified OCaml library containing some basic data structures and algorithms, typically collections of various kinds and graph algorithms and the typical kinds of algorithms which are useful when you implement compilers or theorem provers or things like that. So CFML would be one tool which we can use to develop this library, and other possible tools would be Y3 or Coq itself, or maybe F star. So that's something which we're about to begin. And that's it. Thank you.
How long did it take?
Where's Tan? How long did it take? It took me about 2 weeks to do just the mathematical proof of complexity without any regard to the actual OCaml code. And then Arthur came and did the connection between the mathematical proof and the code, and it took him maybe 1 week, maybe even less. I'm not sure exactly.
It's pretty speedy.
Well, Arthur is no normal.
Yeah, of course.
So,
Yeah, of course. Arthur is the author of CFML, and he's also a very smart guy. So, someone who doesn't know CFML would need more time to get acquainted with it. And at the moment, CFML is not very well documented. But as part of this project, which I mentioned, we intend to produce more documentation on how to use the tool. Yes.
In the version where you have the particular constants like 3 alpha of n and so on, it's sort of a big O notation. If you refactor the code a little bit in a way that introduces more function calls, that's going to change the constant.
Yes, that's the trouble with the concrete cost. It's not modular because some internal change in the code becomes visible to the outside because the concrete number of credits changes. So that's the main motivation for introducing the big O notation.
I see. So that would allow you to hide the internal.
Once you say it's O of alpha of n, then you're free to do as many function calls as you like internally, as long as you preserve the asymptotic complexity.
And when you pass in functions to a higher order function, that's going to get called by the higher order function.
So when you write down a specification for a fold function, for instance, which does a loop, you could equip it with several different specifications, which will be useful in different scenarios. For instance, the most precise specification would say the cost of fold f is the sum of the costs of all individual invocations of f. That would be the most precise specification, but not very easy to use. And you could also derive from that another specification which says if f is constant time, for instance, then the cost of fold f is just O of n, where n is the number of elements. And you could have other specifications in between, like whatever the cost of f, if you have a bound on it, then the cost of the loop is n times this bound. So you can prove several specs for the same function, and the client is then free to choose whichever one is most convenient. So that's the way we plan to approach working with high-order functions. Yes.
I can see after seeing the talk why you're tempted to go to the O of O notation, but when you first introduced the 3 alpha plus 6, I thought, oh, that's going to be very useful. It's useful to see the concepts if they were meaningful. If it was actually talking about x86 instructions or something, or
Yes,
or
maybe it would be
seconds or something. It would be useful to lift that to expose that. If the
yes, if it was an actual estimate of the worst case execution time, then maybe it would be useful. Yeah.
But I just say you may not want to just throw away everything and make it OAuth, because ultimately maybe you want to have a model of the machine and the
Then if we wanted to do that, I guess we would need to try and have more automation in the process of gathering these little constants.
Right.
Because at the moment it's tolerable to do it by hand because we seldom pay. We only pay at function calls. But if we had to pay for every single instruction, then we would have to compute the sums of all these costs. And we would have to automate it, otherwise it would be intolerable.
You said that you kind of had this division of labor where you spend a couple of weeks doing the mathematical proof. I'm wondering how that division of labor worked out, because it seems like you need to reason about the structure of the code with the specific function calls that are being made and so on to come up with these constants. So how were you able to do it just independently of the code initially?
Well, it was fairly easy because abstractly you have an idea of what union find is. So let me go back to the slide where I showed this invariant. You can describe the algorithm abstractly in terms of these things. The graph F, which describes the edges in memory, it's just a relation. It has type element to prop. And similarly, you have this function K, which is just a function of every element to its rank, and so on. So you can prove many properties of these things abstractly. I can define union and find at this level. I can say what's the effect of union and find on F, K, and R abstractly. And then I can prove many lemmas about what these operations do and how much time, so to speak, they take. So that's what I did without even looking at the code. So you can do all of this math independently. And then it's fairly easy to connect that with the actual OCaml code using CFML. Basically, CFML extracts proof obligations, and every obligation is proven by one of the lemmas which you have done at the mathematical level ahead of time.
But even the amount of time it takes at this level, you can reason.
Yes, you have to artificially introduce something that allows you to reason about the time. For instance, to reason about the cost of find, I have defined an inductive predicate, which means we are doing n steps of path compression. And once I have this predicate, I can give a bound on n, for instance. I can prove that at most this many steps of path compression are needed. So that's where the hard part of the proof goes in. And then it's very easy to connect that to what the actual code does. All right. Yeah, thank you.